So last time we talked about functors. Functors are these mappings between categories. And endofunctors are mappings within a category. But they follow the same rules. So remember, functor is sort of like lots of functions put together. There's one major function that maps objects, and it's an actual function only if the category is small. So the category in which objects form a set, and then a functor is just a function on objects. But it also has to preserve the structure of the category. And this was like the most important part that we have learned, that we want to understand what it means to preserve structure. And nothing defines it better as a functor. So a functor maps not only objects, which are like the dots, but also maps the connections between objects, which are morphisms or arrows, right? So for every pair of objects, we have this set of arrows between them, or morphisms, right? Which is called a home set. And as these two ends of a home set are mapped from one category to another, we define also a mapping of these morphisms, or mapping between home sets. And since home sets are sets, at least in a locally small category, right? Since these are sets, that's also a function, right? So for every home set there is a function. As many home sets we have in a category, for each of them there is a function that maps this home set to the corresponding home set in the second category. That means preserving connections between objects. If there is no connection between two objects in the original category, well, we will not map this connection, right? But if there is one, we will never break it. There has to be a connection in the corresponding category, right? So like, if you have a second category in which you have no connections between objects, for instance, we talked about this discrete category, where there is no connections between objects. Well, then you cannot have a functor, non-trivial functor, into that category, right? From a non-trivial category to a discrete category, unless you just map everything into a single object and all the morphisms you map into a single morphism. You can do that. But that's a kind of trivial functor, a constant functor, which is also important. And also we said that, you know, while preserving connections, we also want to preserve structure. That is the connections plus the way how we combine connections, meaning composition, right? So a functor has to preserve composition, and it has to preserve identity. So functor really preserves the categorical structure, because category is composition and identity. So it preserves composition, preserves identity. So it preserves the structure. That's very important, preserving structure. Now, since functors are built from functions, and again, I have to always say, at least for small categories, right? We know that functions compose, right? That's like the main thing about functions, they compose. So since a functor is a bunch of functions, we can maybe compose functors, right? So like if we have one category C, right, and we have another category D, and a functor that goes from here to here, right? So it maps objects. So suppose that we have a functor F, right? It maps objects. Let's start with objects, right? And then we have some category E, and and you know, another functor G that maps objects. Right? Now, if we have so this gives us, you know, one function that maps objects. We can create a shortcut function, right, that goes directly from C to E, and it's just a composition of these two functions, right? So we know how to compose functions on objects. That's easy, right? Now we can do the same for a morphism. So we have a morphism here, and it's mapped into a morphism here, and this morphism can be mapped using G to this morphism. So if this is F, well, this is F acting on F, and this is G acting on F, acting on F, right? So if this is A, this is F acting on A, and this is G acting on F, acting on A, and so on, right? So I'm not doing anything special. It sort of falls out from the way we compose functions, right? Since this is a function on object, this is a function on home set, it just falls out. So functor composition is just very easy to define, right? And obviously it preserves the structure because each of them preserves the structure. So the composite functor, and we'll call this functor, you know, we'll just call this functor G after F. So there is a functor, let me put it in red. This is a functor G after F. And it maps objects like this, right? And maps morphisms like this. So we can just define G after F like this, and of course, so we have composition of functors. So we have composition. Do we have identity? Well, do we have an identity functor? What an identity functor would be something that goes from you know, C back to C, and it maps each object back to itself, right? And each morphism to itself. So that will be an identity functor. Identity functor maps everything to itself, right? Object to object, morphism to morphism, without changing anything. And obviously, if you have an identity functor, this identity functor, which is actually an endo functor because it doesn't get you out of the category, this identity endo functor, when you compose it with any other functor, it will give you back that functor. So it is really an identity with respect to the composition of functors, right? So whatever we learned about composition of functions, you know, we can say the same about composition of functors, and whatever we learned about identity functions, you know, we can say the same about the identity functors, right? So great, so we have functors compose. This composition is obviously associative because function composition is associative, right? Has unit, has identity. So, am I seeing something? Right? Like,
It's a category. Yeah.
it's a category, yes. Yeah. Wow. So, what is this category? Oh, it's a category in which functors are morphisms, right? And what are the objects? Categories. Okay, so a category in which functors are morphisms and categories are objects has a name. It's called cat. Okay, so it's a category of categories with functors as morphisms. Okay, there are some subtleties, and I don't want to get into them. The subtlety here being, well, you know, a category can be small or it can be large, right? So we are sort of covering here small categories, not worrying about what happens when a category is large. And things get a little bit more complicated, right? So in many mathematical books, you'll find that cat is really a category of small categories. And if you want to talk about category of large categories, then you have to use a slightly more powerful mechanism for that. And we'll get to that, you know, maybe not in depth because we don't really need that as programmers, right? But just to know that something like that exists. Okay. Now let me give you an example of composition of functors in programming, right? So, for instance, I want to compose two functors. Well, functors are these containers for us, right? Endofunctors. So let's combine two such functors that we know about, maybe and list. Okay, and actually it's a useful combination because if we want to define, you know, there is this function called tail in Haskell. Tail, and tail takes a list of some A's, right, and returns a list of A's. And it's defined so that it just throws away the head of the list, right? It just returns the tail. So it's well defined only for lists that are non-empty, right? And what if the list is empty? Well, your program dies. Okay, and this thing is in the standard library, right? So be careful, right? Now the only reason why people use it and it's in Prelude is because it's more optimal, right? Because otherwise you would have to always check, is my list empty or non-empty? But this is sort of like the null pointer thing, right? Achilles heel of Prelude. There's another one called head, which has the same problem, right? But if we are, you know, if we don't care about performance and we want to be 100% sure, then let's define something called safe tail. That takes into account the possibility that the list can be empty. So for any list, really, for any list, it will return us something like an exception, but in the type system without using exceptions, which is maybe. And maybe is sort of like, you know, normally return me just the stuff, and if you have a problem, return nothing. So maybe list of everything. Okay? So how would we define this? Well, we would define this well, okay, so we could go ahead and define it. So we would define it for an empty list. No, okay, well, yeah, so we would define it for an empty list, right? And that would return nothing. That's the exceptional case. And for anything that contains x colon x's, that's how you pattern match a list that has a head and a tail. So x is of type A, x is a list of A's, which could be empty, by the way. That's okay, right? And we would return just x's, right? So we skip the head and just return. So we have applied two functors, one on top of another. So we have actually composed the maybe functor after the list functor, right? You know that list is a functor and maybe is a functor. So maybe list is also a functor. It's a composition of two functors. It's a functor, right? So how would we define an f-map? So if we apply this safe tail, we get this maybe list, and we'd say, you know, but we actually wanted to, like, you know, it's a list of integers or doubles, and we want to square it, every element, right? So how would we apply a function square to the contents of this maybe list? Well, we could just go ahead and define it, you know, for all these special, all these cases when it's nothing, and then do nothing, and so on. But we have already defined fmap, right? We have fmap for maybe, and we have fmap for list. So if we want to define fmap for maybe list, right? We would do something. Okay, so let me just say I want to apply this function square to a maybe list of integers. I have maybe list of int. Okay, and I want to apply the function square. So I have some maybe i's. Okay, let's call it this, right? And I want to apply square, function that's called square, and it takes an int to an int, right? And just squares it. So I would have to, since this is a maybe, I would have to apply miss acting on SQ, miss taking, no. So what do I want? I want to apply SQ to miss, right? So I would do fmap something acting on miss, okay? But what is this something? It would have to be a function that goes under the maybe, right? Because what fmap does, it just goes inside of the functor and applies. So, but what's under maybe is a list. So if I want to apply square to a list, right, I would have to apply fmap to this list, right? So I have to pass it a function that's actually an fmap of this square and apply it to this, right? So I'm just going through two layers of containership, right? So I'm sneaking this function under the maybe, and this function, when acting on a list, sneaks square and under the list, right? So altogether this works. And this could be written as really fmap dot fmap acting on this. So this is how you compose functors in Haskell. You know, you just compose fmaps. Okay. And now, I mentioned previously, I said something about that most type constructors that you would normally use or come up with in Haskell, most of these type constructors are sort of automatically functorial. It's like really not so easy to come up with something that is not a functor. What it means is that, you know, you have a type constructor and defining fmap for it kind of falls out. automatically, right? It's like most data structures are kind of regular in this sense. And so what it really means is that data structures that are algebraic data structures. Remember algebraic data structures? All these algebraic data structures are automatically functorial. So how do you form algebraic data structures? You form them using things like products or sums, right? And you apply them to these unit or void. Well, usually we don't use void, but theoretically we could. But usually we apply it to either unit or we apply it to a type variable, right? So, what I want to show is now that if you create an algebraic data type using these operations, then you automatically have a functor. So we have to start by asking ourselves the question, is a product a functor? Okay, well that's kind of weird question, right? What does it mean? Is a product a functor? So let's try to ask this question more precisely. So a product of two types, right? We can write it as a pair in Haskell. It's a pair A, B. A and B are the two types, and a product is just a pair, right? I showed you there are many ways of constructing product types, but this is like the canonical one, right? This can be rewritten really as a type constructor in this form, acting on A and B, right? Because this is sort of, well, it's not really infix notation. Right? This is sort of infix outfix notation, very special notation. But we can always write it as in this form. So we could ask ourselves the question: is this a functor in B? Like if we fix A, is this a functor in B? And it kind of obviously is a functor in B, right? Because it's a type constructor. If we fix A, then it's a type constructor in B, right? So we can construct a type by pairing it with some fixed type. Now, if we want to apply a function to it, right, we will just apply the function to the second element of the pair, right? And it kind of works, right? So if we have the function that goes from A to B, right, we can lift it to, let's say, what letter should I use? Let's say E, okay? EA, and this is EB. So I'm pairing with some E, some fixed type, right? So if I have a function from A to B, I can apply this function, I can lift this function to, let's call it fmap f, where this fmap takes E x and produces E fx, right? So I'm acting with this function on the second component of the pair. And that's my lifted, so this is my fmap f. Acting on some E x. Well, okay, so really that's what I mean, right? If we want this to be Haskell. So fmap f x produces. So it is functorial in the second argument, sort of easily. And you can think of this, you know, a pair is really a container. It contains the second element inside of it, right? In fact, it's a very nice container because it always contains the second element. You cannot construct a pair without providing the second element. So it's always there. Now, by the same token, we could like invert this stuff, flip it, and say, but it's also functorial in the first argument, right? So, but is it functorial like in these two arguments at the same time? Like, can we maybe generalize the functor and say it's a functor of two arguments, right? Just like we have functions of two arguments, can't we have a functor of two arguments? So like this would be a functor in A and B. So it's a functor that takes two types and produces a third type. And indeed we can do this, right? And go ahead. Except that we don't really have to. Well, in Haskell we do, but in category theory we can reuse stuff. Okay, we can reuse stuff. Once we have the definition of a functor, then instead of extending the definition of a functor, why don't we just play with categories? Okay? So we can define a functor that acts on a pair of categories. Okay? So we take one object from one category, another object from another category. Here both A and B are from the same category because we are in Haskell. We only have one category. But in general, you know, A could be from one category, B could be from another category. So we can define something that is a product of two categories, right? And if we can define a product of two categories, then a functor from a product of two categories would be equivalent to a functor of two arguments. One from one category and one from another category. Just like we do with functions, you know. What's a function of two arguments? It's a function that takes a pair, right? Which is a product, Cartesian product, right? But now, wait a moment. But we know that products, in category theory, products are these complicated beasts, right? We defined what a product in a category is, and it was using a universal construction, right? And now I'm saying I want to do something even bigger. I want to take a product of two categories. Isn't that something horrible, right? Monstrous, that will require like super universal construction on category of all categories. Well, it turns out that a product of two categories is really easy to define. Easier than a product inside a category. Why? Because, at least for small categories, right? Objects in a category form sets. So I can say, okay, let me take two categories, C and D, right? We take an object from C and an object from D, and we can form a pair CD. So we construct a new category that we will call C cross D, in which objects are pairs of objects, right? So really, the objects here in this category are a Cartesian product of the sets of objects in these two categories, right? So it's really not difficult because objects form sets here in small categories, right? Since they form sets, then I can just cross product them, right? Cartesian product, and I have a product category. Well, I don't yet, right? What else do I need? Morphisms, right? Yeah. Yeah, so if I have a morphism here and the morphism here, so let's call it C prime, right? So I have an object C prime and I have an object D prime, right? And I have F and G, right? So object C prime and D prime, they form a pair here, C prime, D prime. So what's a morphism between these two pairs? Well, it's a pair of morphisms, right? And again, this is easy to do this pairing because these guys are elements of home sets, and home sets are sets. So I can do a Cartesian product of this home set with this home set, and I'm getting a set of pairs of morphisms. So F, comma, G is a morphism here, right? So I have a new category called the product category, and I have defined what are the objects in this category. I have defined what are morphisms in this category. Do you want me to write a composition in this category? Yeah? Yeah? No problem, right? So if I want to compose, if I want to compose, let's say, Fg with some F prime, comma, G prime, right? Well, this will be just F prime after F, comma, G prime after G. And I have composition, right? And since this composition is just the composition of original morphisms under the hood, it's obviously associative, right? Do I have an identity morphism? Right, an identity morphism would be ID, comma, ID, right? This is an ID in C, this is an ID in D. So if I have an ID at a pair AB, it's created from ID at A and ID at B, right? So I have identity morphisms, I have composition of morphisms. So a product category is really a very simple construction. Just sort of falls out without any work, right? So now when I have a product category, it's just a category, and I can say, well, I can define a functor that goes from this product category. So I can define a functor that goes from C cross D to some E, right? And that's just a good functor, right? But then I can look under the hood and see, okay, so what does it really mean? Oh, it means that to every pair of objects, for every pair of objects, I pick an object here, right? So it maps a pair of objects from C and D to an object in E. And on morphisms, right, if I look under the hood, a morphism in C cross D is a pair of morphisms. So it maps a pair of morphisms from C cross D into a morphism in E. Right? But it has a name actually. So a functor from C cross D to E, if you look under the hood, then it's called a bifunctor. Okay, so it has a name, bifunctor. So a bifunctor is just a functor from a product category. That's all. Now, if we want to do this in Haskell, we would say, okay, so we now have to lift a morphism from a product category. Now here we are talking, since we are in Haskell, this will be a product of the same category with itself, right? So it's you know, C cross C, C cross C goes into C, right? Where C is actually our category of types and functions, right? But notice that now we are actually talking about a functor. If we look at it this way, we are talking about a functor that's not from set to set or Hask to Hask, right? It's a functor from some other category to Hask. It's a functor from a product of two Hasks, right? Or two sets. So we are sort of already getting outside of Hask, and we are getting into Hask square, right? Hask cross square, cross Hask, right? So we can talk about this bifunctor as being a functor from a product category, or we can peek under the hood and say, okay, but what does it mean in terms of functions that we know, right? Well, it means that you know, we have a mapping from two types into a type. Oh, wait a moment, that looks sort of like this, right? It's a mapping that takes two types and produces a new type, which is a pair of these two. Okay, so this is actually an example, good example. But what about morphisms? Okay, so a morphism in the product category, it's a pair of functions, right? So we are lifting two functions at the same time, right? So if we want to define a bifunctor in Haskell, right? And just like functor, it will be defined as a class, right? So it's a class bifunctor. Where, right? And so it will have to have this way of lifting two functions at the same time, right? So we could write it as a lifting of a pair of functions, but in Haskell we really don't like to write functions that act on pairs. Instead we do currying, and we just write a function of two arguments. So this function, this higher order function corresponding to fmap, will be called bimap. Bimap takes two functions. So it takes a function to, let's say, a to a prime maybe, right? And another function from b to b prime. So in Haskell, you can actually use primes in names of variables. It's so convenient. And it lifts it to a, okay, well, let me call it f. Because if I call it b, then I have to. So it takes a b into f a prime. Oh, okay. I have to like maybe split this. Okay. Because I don't want to get outside of the. So it takes f a b to f a prime b prime, right? And it's. It would be kind of hard to understand this without maybe a picture. So, do we need a picture, or is it understandable? So f is this bifunctor, right? It takes two arguments, two types, a and b, right? Now one function turns A into A prime, the other function takes B into B prime. So we get these two functions under the hood, and they transform AB into A prime, B prime. And the compiler at this point figures out, since F is acting on two types, that F actually takes two types as arguments. Okay? Just like previously when we were defining a functor, the compiler figured out that it takes a type as an argument, so it's a type constructor. Here's a type constructor that takes two types. Okay? And in particular, you know, we can define this product as a bifunctor. So a product is a bifunctor, right? And you can easily, okay, so you have two functions, one function, second function. What does it do to a product? Well, it applies first function to the first component and second function to the second component, right? It's kind of trivial. So applies them in parallel to these two components. Okay, so now we know that the product is functorial. And by the way, if something is a bifunctor, then it's automatically functorial in the first component if you fix the second one, and functorial in the second component if you fix the first one. And you can get it from bimap just by putting an ID here, identity here, or identity here. And you'll get that two F maps out of it. The first argument, the second argument. Okay, so product is bifunctorial. Excellent. Now we have to think, what about sum? Do we have to go through this construction and come up with like a sum of two categories? Never heard of something like this. Okay, no worries, no worries. We don't have to find another. What happens is that we can use the same bifunctor idea for a sum, right? So either AB, that's the sum type, like the canonical sum type of two types, right? Either AB is actually a bifunctor, okay? So we can define the action of two functions on either AB, right? So either AB takes a pair of types, right? So it takes a pair of types from a product category, right? It's a function of two arguments. So it takes a pair, or in the curried form, it just takes two arguments, right? Takes two types and produces a third type of either A and B. And it is also functorial. So you can apply these two functions, right? And the first function will be applied to A, and the second function will be applied to B. Very easy, right?
Could you use some, in the categorical view of it, could you view it as some operation on the opposite category? Or the opposite of the product?
You mean
C cross C?
No, actually, no, I'm not doing this. What I'm doing is,
but I'm curious.
I'm doing something else, okay? I'm saying these constructs that we, well, actually what I did here is I just did a Haskell part, right? I didn't say stuff about categories, really. Just the Haskell category. But in general, so what we want to have in general is to say that if we have a product in a category, then this product is actually a bifunctor. And it's a bifunctor of this type, C cross C going into C, right? So we have an example of this. Well, here we have two examples in Hask. One is the product in Hask, and one is the sum in Hask. They both are bifunctors, like this, okay? So actually, I want to talk about this, right? So actually, you can show that in any category, if you have products defined, you have to have products defined for every pair of objects, right? So a category in which products are defined for every pair of objects are called Cartesian categories, right? So if you have a Cartesian category in which you have products for every pair of objects, then this product is a bifunctor of this type, C cross C to C. So it takes two objects as an argument, right, and produces a third object. And this mapping from these two objects into this third object, which is the product, is actually a bifunctor, right? And the same is true about coproduct. So a coproduct is also a bifunctor. It takes two types and produces a third. Okay. Now you probably want me to show this, right? So when I say it's a bifunctor, well, it means that there is I can define it on morphisms as well. Right? Because so far, we define products for objects. But now we have to define them for morphisms as well. Right? Well, that's a challenge. So what do we want to prove? We want to prove that if we have, let's say we have A and B, right? And there is a product A cross B in our category, right? Which means that we have these two projections, P and Q. So this is the universal, so suppose that we have a universal construction that constructed this product of A and B, right? But now we have morphisms F from A to A prime, let's say, and we have a morphism from B to B prime. Let's call it G, right? Now for A prime and B prime, we can also construct a product, right? Because I said you can construct a product for any pair of objects. So in particular for A prime and B prime. So there will be an object called A prime cross B prime with some two projections. Well, let's call them P prime and Q prime. Okay? Are you with me so far? Right? Now, if I want to show that this is a bifunctor, I have to show that I can lift this pair, F and G, to something that acts here. Okay? From A cross B to A prime, B prime. Now I did this in Haskell, that was easy. I just applied F to A and G to B and I got this mapping, right? But in general, how can I do this? Any ideas? Well, I can't, the only thing at my disposal is the definition of a product. And the definition of a product says, the definition of product is the universal construction, right? So it says that if I have, you know, any other candidate, then there's a unique morphism from that candidate to the actual thing. So let's look at this, okay? Let's look at this and see. See? The product of A prime and B prime is this guy. Let's think of this as another candidate, right? It's a candidate that has two projections. One projection is F after P, right? F after P is a projection here. And here's a projection called G after Q. G after Q. Okay? So A cross B becomes a candidate for a product of A prime, B prime. Right? But the product of A prime, B prime is this guy. We know that, right? By definition, we said this is the product. So this is a fake candidate, right? But for every fake candidate, there is a unique arrow from the fake candidate to the actual guy, right? So there is a unique arrow here. I'm going to call this arrow here, I'm going to call this arrow F cross G. That's my definition. That's my lifting, okay? I have just constructed this arrow using universal construction. And I call this arrow F cross G. Yes?
Sorry, dumb question, but I thought when we created C cross D, we said it was a Cartesian product. But out here, you're saying like this is a product in the sense of a category, like inside the category.
Okay, because I'm juggling several things at once, right? So, what I'm trying to say is that this mapping A comma B, which is a member of C cross C, to A cross B, which is a member of C, is a bifunctor. Okay? So this is how I got this A and B.
Right.
I got them as a pair from the product category. Right?
Right.
So for every pair, I have a product. That's why, you know, I need a Cartesian category so that I can do this. I can do, say, for every pair, give me a product.
Right.
For every pair, give me a product. Where do I get these pairs? Well, I get them from C cross C, right? So for every pair from C cross C, I get a product. And now I want to show that this mapping from C cross C to C is a bifunctor. And that's what I did. Okay?
I have another dumb question. So, when you spoke about either AB being a bifunctor, either AB contains only one of those two, though, right? So, I guess I'm having some trouble visualizing how you would try bind.
Well, so if you want to define a bifunctor for either AB, right, you would have to do case analysis,
okay.
right?
Right.
It's either left or right. So if it's left, apply F.
Right.
If it's right, apply G. Disregard F, apply G, right?
Yeah.
That's how it works. Okay. And if we did the same kind of analysis on the diagram for coproduct, you know, it would work also, but in the opposite category, right? So indeed, these are bifunctors, both product, categorical product now, not just a pair. You know, that's a categorical product. That's in a Cartesian category. It's a bifunctor. And if we have a coproduct in a category, so it's a like co-Cartesian category, right? Then the coproduct is a bifunctor as well. Okay? So we can have a category that has a bifunctor that's more general than just product or coproduct. Maybe there are other bifunctors that are, you know, that we don't know about. So these categories that have a bifunctor like this are called monoidal categories. Okay? But of course, for them to be monoidal categories, they would have to have a unit as well. Okay? So let's take a break now, and I'll show you the unit after the break. Okay?